last lecture. So in the last lecture, we talked about the band diagram of the silicon. And this is a very important concept. And we use the electron's energy as the band diagram. So here we have two bands, valence band and conduction band. So here we're interested in the electrons in the conduction band because they can move and conduct current. And also we are interested in the holes in the valence band because they can also move and conduct current. And between the conduction band and valence band, we have this band gap, Eg. In silicon is 1.1 electron volts. So this is not an energy level which we don't allow any electrons or holes. So we have those three level here, EC, which is edge of the conduction band, EV is edge of the valence band, and EF, which is a conceptual level, we call it Fermi level, to describe the probability to find the electron at a particular energy level. And we know that at the Fermi level, the probability is half. And then for other energy levels, we need to use the Fermi function to determine this probability. And the Fermi function is given here. And here we show the plot for the Fermi function. And we know that if the energy is way above the Fermi level, then the probability is 0. Or if the energy is way below the Fermi level, then it's 1. And then in the middle, we will have this transition. And this transition region depends on the temperature. So if you have larger temperature, for example here, the T3 larger than T1, larger than T2, larger than T1. So the higher the temperature, the more broadened this transition region is. So this is the Fermi function. And then we also talk about the Boltzmann approximation for the Fermi function. So essentially we are looking at when the energy level is way above the Fermi level or way below the Fermi level, then we can approximate this Fermi function as the Boltzmann function. So essentially we are looking at the tail of this function. And we think this is like an exponential tail because the Boltzmann function is an exponential function. So we look at this tail, then we are looking at this tail of the exponential function. Here we just rotate the x and y. So we see the regular exponential function. We are looking at this tail. Essentially, we are looking here. So why are we interested in this Boltzmann approximation? Because typically you will see that the EC is way above EF, and the EV is way below EF. So that means when we describe the electrons in the conduction band, those electrons are in the tail of that Fermi function. So that's why we are interested in this Boltzmann approximation. So you can use the Boltzmann approximation to describe those tail, either here or here. But if the energy is in the middle, close to the EF, then you cannot use that approximation. So you have to use the Fermi function to describe the transition region in the middle. So this is the Fermi function. It tells you the probability of finding electrons at certain energy level. But one more thing we need to consider is the available states for the electrons to occupy. So for example, we have this example. So here is the available states of the electrons at different energy level. And we have an energy in the last lecture. We say that this is available states like the seats in the classroom, right? And then you guys are like electrons, so you need to find where to occupy in those available states. And then here the density of states describe how dense those states are with respect to the energy level. So this is what we have here. For the electron, we have this density of states with this kind of shape above the EC. So the higher the energy level, that means you have more available states. So this is the density of states. And similarly for the holes, we will have the density of states for the holes below the valence band edge, EV. And then we use the density of states and the Fermi function to determine the electron density in the conduction band. So we look at the multiplication of the density of states and the Fermi function, and then get this distribution of the electron in the conduction band. And further, we did an approximation, assuming that all the electrons are accumulated as edge at EC level, and then we give an effective density of states for this EC level. We call it NC, and then this is effective density of states in the conduction band. If we do this approximation, then we will get this equation for the density of electron in the conduction band. N equals to NC multiplied by this exponential function, which is determined by the energy difference between the EC and the EF, and then divided by the KT, which is thermal energy. So NC is a constant for silicon, and the number is shown here. Similarly, we can get the hole density using similar formula here, and then we have another constant NV, the effective density of states of the valence band. So here is a summary. And essentially, we are looking at the energy difference between the EC and EF to determine the electron density. And then we're looking at the energy difference between EF and EV to determine the hole density. So this is what we discussed in the last lecture. Any questions? So those two equations are very important, because from those two equations we can derive something more here for the intrinsic semiconductor. Intrinsic means no doping, pure silicon, for example. So if it's no doping, then N equals to P, because no doping, then you get one electron, then you get one hole when you break the bond. So you get a pair of electron and hole, then N equals to P. So if N equals to P, then you can derive that the Fermi level is almost in the middle of the band gap. So you can do this by using N equals to P. Basically, you use those two equations, they equal to each other. And then here we need to assume that NC is roughly the same as NV. Although they are a little bit different, but the orders of magnitude is the same. Both of them are 10 to the power 19. So then if you take the log scale, then you only care about the orders of magnitude. Then if you take the log scale of those two equations here, then you get the EF minus EC roughly equals to EV minus EC. Then you move the, EV minus EF. Then you move the EF to the other side, then you get this EC plus EV divided by 2. So that tells you the EF is roughly in the middle of the band gap. If you look at the numbers for silicon, so the EG here is 1.1 EV, and then the Fermi level, if it's intrinsic, then the distance here is about 0.55 EV. And also we can look at the NP per dot using those equations here. You can multiply N and P, and then if you do that, here you can see that EF cancel each other. Then what is left is just the EG. So from here we can get the intrinsic carrier density Ni, and then the Ni is this square root of NC NV, and then the exponential to the half of the band gap over KT. And if you plug in the numbers NV and EG, and with the room temperature KT, then you will get the Ni 1.5 times 10 to the power 10 centimeter cube at room temperature. Of course, this number depends on the temperature. So you can say that NP product is a constant. So this is true. No matter what doping you have, either N-type doping or P-type doping, and no matter what, the NP product is a constant. So this is also another important conclusion. So any questions?
What is EI?
EI is defined as intrinsic carrier density when you talk about this intrinsic semiconductor. N equals to P equals to Ni. And it corresponds to the Fermi level in the middle. Yes. And sometimes this Fermi level in the middle, we also call it EI, intrinsic Fermi level. Okay, so here, this is again the NP product, the derivation of that, and then we will get this NP product equals to Ni squared, and this Ni is given by this formula, and then Ni at room temperature for the silicon is roughly this number. Of course, if you want to be careful, then it's 1.5 times 10 to the power 10. So it's 1.5 times that. Okay, so if we have those information, then let's do this question. What is the whole concentration in an N-type semiconductor with 10 to the power 15 per centimeter cube of donors? So this is similar question in your homework. In the last question of your homework. So how do we do this? So first of all, this is N-type semiconductor. That means you have donors. And then if you have donors, then the donors will contribute electrons. So one donor, one electron. Then you will get the electron density equals to the donor density. And the donor density is given here to the power 15. And also this N-type semiconductor, we know that the electron is a majority carrier. So because this is more than whole. So we think electron is a majority carrier. Then the question asks you for the whole density. What is the P number there? And P is minority. So here, as I said, no matter what doping level you have, the NP product is a constant. NP equals to Ni squared. So you can use that to get the P, right? So from this equation here, P equals to Ni squared divided by N, and you can plug in the Ni squared. Of course, here if you roughly do this, it's 10 to the power 10. If you want to do it carefully, you carry the 1.5. But here let's do a rough estimation. If you just use 10 to the power 10, then the Ni squared will be 10 to the power 20. And then divided by 10 to the power 15. Then you get 10 to the power 5 for the P. So you see the whole density is much lower than the electron density. If you look at the orders of magnitude, one is 15, one is 5. Right? So the whole density is like 10 orders lower than the electron density. So that's why electron is majority and whole is a minority in this case. This is because you have N-type doping. You increase the electron and reduce the hole. Any questions here? And here another, let's say, a tip for you to check your solution. Very easy, because always you have this. If you just check the orders of magnitude, then the Ni squared will always give you the order, let's say 20. And then if your doping, let's say for the n-type doping, give you n to the order of 15, then the other one must be 5, because it's 5 plus 15 equals to 20. So if we change this question, if the donor density becomes 16, 10 to the power 16, you can easily get the whole density 10 to the power 4, because 4 plus 16 equals to 20, because that sum is a constant. So 5 plus 15, 4 plus 16, or 3 plus 17. So it's always like that kind of combination. And then intrinsic one, both of them will be 10, right? 10 plus 10. That is intrinsic, because A equals to P. Then both of them are 10 to the power 10. All right, so this is this. Any question?
The 10 to the 10 for Ni, is that a constant that we should remember, or is that specific to this problem?
This is specific to silicon at room temperature. Yeah.
So this would apply to a lot more problems than just this one?
So if your question meets this condition, we are asking silicon, we are asking room temperature, yes. Of course, if we are asking that at different temperature, then that's different. Okay, so let's look at the extrinsic semiconductor. That is with doping. So with doping, actually what we are doing here is to move the Fermi level up and down. If we have n-type doping, so can you guess the EF is closer to EC or closer to EV? For n-type. Yeah, close to conduction band. So here, you can imagine here, so from this equation, if you want to higher n-type doping, that means you will have more electrons. N number is large. If n number is large, you want to minimize the distance between EF and EC, because this is negative term. You want to minimize this to get a larger n. So that means EF will be closer to EC. And we can have two conditions. For example, you have two doping density, ND1, ND2. If ND1 is larger than ND2, then you have two Fermi level. Which one is higher, EF1 or EF2?
What is this?
So if you have two doping density, ND1 is larger than ND2, two doping.
What doping you do, the more closer you do.
So then the question is which one has higher Fermi level? EF1 or EF2? You have two cases?
Yeah.
EF1. Okay. So the higher n-type doping, the closer EF to the EC. So if you want to draw that, then if this is EF2, then your EF1 will be somewhere closer to the EC. And similarly, if we have the condition for the p-type doping, Na1 larger than Na2, then the EF1, EF2, which one is higher? Which one is higher? So this is opposite, because for the p-type doping, if you have higher p-type doping, that means more holes. More holes means the EF is closer to the EV, the valence band. So if you draw that, if this is your EF2, then your EF1 will be somewhere here. Any questions? All right, so then let's look at this problem. And this will be similar as your last homework. And also this kind of question, I can guarantee you will be in your midterm exam. So you do want to know how to solve this kind of question. So the question here is for silicon. The NC, NV number given, and NI given, and the KT, this is at room temperature. It's in the unit of the electron volts. So it's 26 millieV or 0.026 eV. So this is at room temperature. So the question is, if you have p-type doping with Na, stands for p-type doping density. If the Na is 10 to the power 17, it asks where is the EF. So typically you'll be asked to draw a band diagram with those, let's say, this kind of band diagram. And then you need to label where is the EF quantitatively. That means you are going to give a number. Let's say how much distance, let's say in terms of electron volts, between your EF and the EC or EV. So that's the question here. So how do we do this? Any ideas?
Conversion in mode. And then use an NCE to the equation, EC minus EF, to get EC minus EF and EF minus EF.
Yeah, so we can start from that equation for the whole density. So you know P equals to MV exponential, the EV minus EF over KT. So this is the equation for the whole density. And you know for the p-type doping, whole density is the same as Na, the p-type acceptor density. So then we can move this around. Over KT. And then we need to take a natural log on both sides. If you do that, it will give you over KT. Then you move the KT to the other side. When I say EV minus EF, is KT times natural log NA over NV. Then you can plug in the numbers now. The KT at room temperature is 0.026 electron volts times this natural log NA. What is NA? NA is 10 to 17. And what is NV? NV is this 1.04 times 10 to 19. So if you plug in the numbers, then you will get the solution is negative 0.119 eV. So here, I think in this kind of question, we always use the electron volts, EV, as the unit for the energy level. And the other thing is when you take the log, the base is E, not 10. It's natural log, not log 10. Okay. So then you can get this. And also, why you get a negative sign here? Because 10 to 17 divided by 10 to 19. So this is in here is smaller than 1. So if you take the log with some numbers smaller than 1, you will get a negative sign. So that means the EV is below the EF by this 0.119. So if you draw this band diagram, you need to draw this EC, EV, and we know the band gap for silicon is 1.1. EV. And now this EF will be somewhere here because it's p-type, so EF should be close to the EV. And how close it is this number, 0.119 EV. So that will be your solution for this question. Is it clear? And then the second question here is what is the N, the electron density for this p-type doping? So how do we do this? So we have done that in the previous slide. So you can always use NP product because that is a constant at this temperature. So that means N will be equals to P and Ni squared. Use NP product is Ni squared. And you can plug in the Ni, and in this case, if we do it accurate, we will carry that 1.5. And then the P, which is the same as this Na, will be 17. So you do that, you get 2.25 times 10 to the power 3. Always carry the unit centimeter cube. And you can also double check the order of magnitude, because if one is 17, the other one will be 3. Because 17 plus 3 is 20. Any questions?
So if Na means p-type, what represents n-type?
ND. Because Na, that A is acceptor. ND, that D is donor. You know, donor is like phosphorus in the silicon. That acceptor is like boron in the silicon. All right. So this is your homework.